to the Pierre Bieliavsky, and the title of the talk is Kinematical Algebras and Contact Sub-Riemannian Symmetric Spaces. Please, Pierre.
Thank you. Well, thank you very much for inviting me here. I'm very happy to talk to you. And so today I will tell you about a work that we did together with Nicolas Boulanger, who is a physicist he's a professor in University of Mons in Belgium. And it's about a paper that we recently published in Letters in Mathematical Physics. So my talk will be in several parts, but it will definitely start with a motivation that I have for that kind of things. So that will be the very first part. And then there will be a historical introduction, because I think it is important to say where those things are coming from. And then I slowly go to the precise definitions, and then eventually I will state the main result. So this will be the plan of the thing. So let me first start with the motivation. So the motivation is based on what is called the Mackey's analogy in group representation theory. So let me explain what is a Mackey's analogy. Okay, so it's something that has been suggested or proposed or conjectured. It's very vague conjecture that was proposed by Mackey concerning a correspondence between representations of two groups. Okay, so basically a group G, which is real or complex reductive group, and a group which is a contraction of this group. So let me try to be a little bit more precise. So I start with this real or complex reductive group, Lie group, and the conjecture is the following. So he says that there should exist some kind of net. So it's very vague, you know, the way it was formulated by Mackey. So the conjecture was okay. So there should exist some kind of natural bijection between the unitary dual tempered unitary dual of the starting group G and the unitary dual, full unitary dual of a contraction of it, which is the Cartan motion group. So basically, this contraction is what? You take the maximal compact Lie subgroup of G that you call K, okay? And so you know that G over K is a symmetric space. It's a Riemannian symmetric space. And therefore, the Lie algebra of G decomposes into two parts, okay? As a vector direct sum. The Lie algebra of K, and then a vector part, which is P, which is basically the orthogonal. Suppose, let's say, if G is semi-simple, this is basically the orthogonal of the Lie algebra of K for the Killing form in the Lie algebra. It's called P, right? And so you can, of course, the group K acts on P by the restriction of the adjoint action of K on P. And so you can form the semi-direct product of K and P, where you see P as a vector group, as a abelian Lie group. And so therefore you can, so this is not at all anymore a semi-simple or reductive or whatever. It's really just a semi-direct product of a compact group by an abelian distinguished subgroup P, okay? And you can look at the representation theory of unitary irreducible representation theory of these groups, the unitary dual. And of course, this unitary dual is somehow tractable precisely by Mackey's machinery, right? So of course, this is why certainly he had this fact in his mind when he formulated the conjecture. Okay, so this K semi-direct P is tractable from the point of view of describing the unitary dual by Mackey's method. And so the conjecture says that basically the representations of G are the representations of this contraction, which is called the Cartan motion group. So that was formulated, I think, around the 60s. And it turns out that Nigel Hickson proves it for the case where G is a complex simple group in 208. So this is a very, very late proof, precise proof for that. And so he exhibited somehow a common natural parametrization set of both the unitary tempered dual of G and the unitary dual of this Cartan motion group construction. So that was done by Hickson in 2008. And then recently, Alexandre Avgoustidis proved it in the general case in 2023. So, as you know, the representation theory of a Lie group is very, very close to Poisson and symplectic geometry. Basically, you know, somehow the what should I say, Kirillov or Constant-Souriau program is essentially the idea is essentially to realize the unitary duals of groups or certain groups at least in terms of coadjoint orbits. Okay, so basically, we have some kind of symplectization of symplectization of representation theory for Lie groups. Okay, so that is of course very well known. And yeah, the work we are trying to now in a joint project with Alexandre Avgoustidis is to realize somehow of symplectization of this Mackey's correspondence. So to try to describe this common parametrization set for these representations in terms of symplectic or Poisson geometry. So that is certainly my motivation there. But now let's start to talk a little bit about historical introduction. So first, you have the notion of inertial frame, okay, in mechanics or in special relativity, okay, and the notion of inertial frame gives you the notion of kinematical groups. So let me give an example. Okay, so for example, if you look at Newton's law of mechanics, okay, so you have the notion of inertial observer, okay, which sees the system when there is no exterior force field, when the exterior force field is zero. Okay, he says, okay, there are specifics, very preferred set of class of observers that are inertial observers, which sees the system as a Euclidean geometry. So this is Newton's first law of celestial mechanics. And so the question is, how do you pass from one inertial observer to another one? So you get a group, and this group, as you know, is the Galileo group, which is described here. So, of course, you have something similar in the case of special relativity, where in this case, you get the Poincaré group. So, these groups are typically kinematical group. And so there is a question that was raised in the 60s by Bacry and collaborators, which is to try to describe, okay, all principle of relativity that space-time can accommodate. So, what are all of them? Okay? What is the general notion of inertial frame, and classify them? So that was done. And the object, okay, which is relevant in this question, is of course a 10-dimensional Lie algebra, and this 10-dimensional Lie algebra is of that form. Okay, so it should be a direct sum as vector spaces. So the problem is exactly to determine the structure, the constant. The structure constant bracket of this Lie algebra. But the requirement, the problem is what? The problem is to describe all possible Lie algebras that are vector sum decomposition of several pieces. One piece is SO3, okay, the rotations. Another piece is R3. Okay, so these are the ones that I put here in blue. This is the space. Then the R3 here, which is the momenta, and then R, which is the time. And you want to find all those algebras that satisfy the following conditions. First, the R3s, both of them, the R3 which is here and the R3 which is there, okay, to be the natural representation of SO3. And another thing is that the time should commute with the rotation. And you try to find all of those. Of course, so that was solved. Okay, there is a list that was solved by Bacry and collaborators in '68. But that was the solution was really obtained by brute force. So basically, they took this 10-dimensional Lie algebra, write down the possible relation by turning the machine by computing, okay, the constraint you get by Jacobi identity. So really brute force, and so they get a list of these algebras. And then, of course, you see that this tree, of course, you can let it go in any dimension. Okay, you could define G of D, where you have SOD and not R3, but you have the defining representation of SOD on RD. Okay, and of course you can ask the same problem. But there, okay, this is the classification when D is big and the dimension of space is big. Of course, this problem becomes much more complicated, and that was solved. The classification was solved by O'Farrill in 2018. Okay, he gave a complete classification of these kinematical Lie algebras, where the factor SO3 is not SO3 anymore, but SOD in general. Okay, so this is historically what happens concerning these kinematical Lie algebras. So now let me continue with another thing, which a priori has nothing to do with the first one, which is kinematical Lie algebra. And the point, basically, what the theorem that I want to present today, so is actually that those notions are related. So the second notion I'm talking about is the notion of Carnot-Karateodory space. So from Carnot, okay, in his work on thermodynamics, the beginning of the 19th century, you have a formulation of the first law of thermodynamics, and Carathéodory, in the very beginning of the 20th century, formulated this first law of thermodynamics in terms of a certain contact form condition. So that is what I'm going to talk about. So this thing is, to be precise, this thing is the following. So simply Carnot-Carathéodory, see I put CC. A Carnot-Carathéodory space is what? It's a smooth manifold, okay, on which you have a tangent distribution. That's it. Okay. So that's very, very, very general. And in a very nice work and very profound and huge work by Misha Gromov, which appeared in the publication de l'IHES in 1981, Misha Gromov studies these spaces. And there is a first theorem, which is not really due to Misha, which is a theorem which is attributed very often to Shaw, but in fact, Reshevsky had the theorem 1 year before. So we are talking about the years of 1938. Then later in 89, Gromov has a much more general theorem with a much more conceptual proof. But I would say that the theorem that I'm now stating is due to Reshevsky and Shaw independently in the 30s. So what it is about? Well, when D generates the whole tangent space, what does it mean? It generates the whole tangent space. It means that when you take tangent vector fields D to the distribution, when you take tangent vector fields and you consider brackets of tangent vector fields, you evaluate these brackets at any point, okay? Well, the vector space that is generated by this bracket at any point is the whole tangent space at the point of the manifold. So this is the condition of generating under bracket. And then the theorem is that basically you can locally, if you take a point X, okay, and locally you can always join every point that is sufficiently close to X by a curve that is horizontal, meaning that the tangent vector, the velocity, the speed, okay, the velocity field, tangent vector along the curve is always in the distribution D. Okay, so call a horizontal curve. You can always do that as soon as you have bracket generation of the tangent vector. So please, if you have any question, of course, you just ask. You can, of course, interrupt me. No problem. Okay, so that's the first thing about Carnot-Carathéodory spaces. In the specific case where D is as far as possible from integrable. Okay, this is this condition of bracket generation is. Well, let me give you an example. So the example is that the Heisenberg group example, but I will explain why I'm talking about the Heisenberg group. So the manifold is R3, and you consider a one form, which is the one form that I just wrote. So in coordinates X, Y, and Z on R3, you consider the form dx plus y dz. So we see that the differential of this form If you look at the differential of this form, what do you get? You get dy wedge dz. Okay, so you see that this differential on the plane yz is symplectic. Okay, and so in particular, if you wedge it with theta, if you wedge theta and d theta, you find something which is a volume form. So in particular, the distribution, which is the kernel of theta, okay, this distribution is as far as possible from integrable, as you can see here, just looking at Frobenius condition. So you are in this situation, very, very simple situation with this distribution, which is not at all integrable. And so what happens? Well, it happens that this distribution is of course generated by the vector fields that I wrote here. Okay, so dy, that's one vector field, and another one which I call f, which is this y dx minus dz. Okay, and the remark is that actually, if you add dx, you see that in fact the EF dx form a base of the Heisenberg-Lie algebra. So here you have an example of a Carnot-Kara-Theodoric space, okay, which is very, very close to the Heisenberg group. So that is an example. Okay, so now let me continue a little bit. So what I said it already, but what I want to tell you today is very roughly that if you consider kinematical Lie algebras, okay, generalization, in fact, of them, which I will describe. If you consider kinematical Lie algebras, and then those are Carnot-Kara-Theodoric spaces. Of course, the word R, okay, should be explained. This is what I'm going to explain in the talk. And reciprocally, if you take Carnot-Kara-Theodoric spaces that are enough symmetric, okay, then actually this symmetric condition is actually a characterization among Carnot-Kara-Theodoric spaces, characterized as Carnot-Kara-Theodoric space that actually correspond to these kinematical Lie algebras in the first statement. Okay, so if you want, the statement is that kinematical Lie algebras, somehow generalized, exactly correspond to these Carnot-Kara-Theodoric space that are symmetric, and symmetric, I will define what it is. Okay, so this is essentially the message of the talk. So now let me enter in some details. Okay, so I will first recall, or maybe tell, if you are not used to this condition, to this definition, what are symmetric spaces, but in a very in a definition which is due to laws. Okay, generally symmetric spaces are described or are defined as homogeneous spaces. Okay, but here I'm not talking about this definition. I'm talking about an equivalent this definition which is due to Otmar laws in 1969, and which is actually completely geometrical rather than Lie algebraic theoretical. So the definition is the following. Symmetric space, okay, what it is, it's a pair of, the first ingredient is a smooth manifold, M, just a smooth manifold, that I consider to be connected here. Okay, I forgot to write that, but in the sequel, the manifold will be considered to be connected. And the map is this second element in the pair is a map. Okay? It's a map that is somehow kind of a multiplication on the manifold. So it's a map that takes two elements, x and y, and that associate to two element points in the manifold, the third one. So this is some kind of multiplication. And what is required in order to have the notion of symmetric space, is that this map should be involutive. Okay, so if you take the map Sx, which is fixed, the first entry of the map S to be a specific point, fixed a point X, okay, any point in the manifold. Well, the map Sx to the square should be the identity. So in particular, the Sx is a diffeomorphism of the manifold. There should be an evolution and of the manifold and should admit, this is the notion of symmetry, of course, that we have in mind. It should admit X, okay? Sx should admit point X as fixed point and isolatedly. So it means that Sx of X is X, okay? But also it means that there should exist a small neighborhood around the point X, okay, a small neighborhood, open neighborhood of the point X in the manifold, where the only point which is fixed in this neighborhood is X. Okay, so the point is X is really isolated fixed point of X in a neighborhood of X. Okay, that's the second condition. And the third condition is a coherence condition. It tells you that if you conjugate, don't forget that Sx squared is the identity, so Sx minus 1 is Sx. So if you conjugate any symmetry, let's say Sy, okay, by another one, Sx, in the group of diffeomorphism of the manifold, then it should be the symmetry centered at the image of X over Y by Sx. This is the condition. And the first example of this that type of space is, of course, Rn with its Euclidean centered symmetries at any point. So the Euclidean geometry, for example, is an example of that. And you have plenty of other examples. So you have, for example, those spaces that I was talking about with my G over K, with G, where G is a reductive, or let's say a simple Lie group, real Lie group, and K maximal compact. These are also symmetric spaces in that sense. It means that you can actually define such a map S in that situation, G over K. So Riemannian symmetric spaces are definitely symmetric spaces. Okay? Hermitian symmetric space. There are many examples, but for sure the first one is the flat space. And so you have a proposition, actually two propositions. The first one is due to laws, okay, in the 60s, 69, or even before. The proposition due to laws is that actually there is always in that situation, you have always geometry. Geometry in the sense that you have a linear connection, which is canonical, which is preferred in that situation. You have precisely, you have a unique linear connection, so meaning a connection in tangent bundle associated to the linear frame bundle, that is invariant under the symmetries in the sense that the symmetries are affine connections. So here, affine maps. So here, I really insist on the fact that this connection is generally not metric. Okay, so this is important here. My symmetric space, okay, you see that in the definition, there is no metric that is involved. Okay, so no metric. However, there is this linear connection. You have a linear preferred connection. And this linear connection is the only one which is invariant under the symmetries. It is defined that way. It exists, defined that way. And it has the property that is torsion free. Okay. And that the curvature tensor is parallel. So if you are used a little bit to that kind of things, you recognize the definition of locally symmetric space, a fine locally symmetric space that you find, for example, the books of Kobayashi and Nomizu. So this is really what you have. However, in this book of Kobayashi and Nomizu, you see that this definition is not the one that they use. This is really due to laws. And now you can wonder, okay, how to find an intrinsic formula for the linear connection. In his proposition, laws construct the connection in a locally. Okay, basically he computes the proofs that he gives the gammas. Okay, the chart. But actually, you have a intrinsic and a global expression, which is the following. So this connection, this Low's connection, let me call this connection the Low's connection. Actually, this connection is defined by the following formula. Okay, so if you take two vector fields, x and y, in a manifold, and a point x, well, if you bracket, okay, those two expression here, so x is the first entry of the bracket, and the second one is y plus its transportation by the differential of x of sx. Okay. If you bracket those two vector fields, you evaluate at point x, then define, and then divide by 2. Then this defines a connection always. And in that situation where S is this symmetric space structure, okay, S here, well, this defines exactly those connections. So you have actually a very, very explicit formula, and this is a very good ingredient to very, very good, a very powerful formula to prove things that I'm going to talk about later. Okay, so this is the notion of symmetric space. Symmetric space manifold with multiplication. Multiplication is has the properties of which are natural when you want to talk about centered symmetries, and then in that case, DAC, you have a connection, and this connection has a very, very simple expression. Okay, so that is what I want to say concerning symmetric space. And now I'm going to talk about a version of symmetric space, which is symplectic. So the definition of symplectic symmetric space is a definition that I gave in my thesis, and my supervisor were Michel Cahen and Simon Guth, and it was given in 1994. So this is a very, very simple definition, completely obvious. The only point is that this definition is, although trivial, interesting. So symplectic symmetric space is a symmetric space in the definition of laws. And omega is a non-degenerate 2 form. It's a non-degenerate 2 form that is invariant under the symmetries. This is the definition of what it is. And then one thing that you can prove immediately is that when you require this condition of being invariant by the symmetries, it implies that this form is actually parallel with respect to the Low's connection. So in particular, this is closed and therefore symplectic. Okay, so a symplectic symmetric space, what it is actually a symmetric space in the sense of laws, together with a symplectic structure that is compatible with the symmetries. This is basically what it is. So let me give you an anticipative example. Okay, so you consider the Poincaré group. Okay, you consider the Poincaré group, and you consider the co-adjoint orbits, okay, that corresponds to the field equation attached to the massive orbits, okay, of the Poincaré group. And those are Klein-Gordon. This is what I'm talking about. Huh? You consider the Klein-Gordon particles, and those are actually symplectic symmetric spaces. So this is an important example. Of course, there are coadjoint orbits, so they are symplectic spaces. Okay, by definition of what is a coadjoint orbit. But the point is that on these massive coadjoint orbits, so those that correspond to representation defining the Klein-Gordon equation, those are actually canonically equipped with such a structure of symmetric space compatible with the symplectic structure. And in that case, okay, so of those massive orbits of the Poincaré group, it turns out that the lowest connection attached to the symplectic symmetric space structure that you have on it, the symplectic connection is never metric. So it is never a Levi-Civita connection for any either neither Riemannian nor pseudo-Riemannian metric on the coadjoint orbit. It is never metric. It's a purely symplectic object. So this is an example which is relevant to what in what I'm going to talk about. So I have this definition now of symplectic symmetric space. This will be an important ingredient. Now let me pass to this version of Carnot-Carathéodory manifolds that were considered by Gromov. Okay. Which is something which is again very well known, which is the notion of sub-Riemannian manifold in the contact situation. So what it is? So let me remind you that a differential one form on a manifold, connected smooth manifold M, okay, is contact when it is as far as possible of integrable. Okay. I mean, the distribution defined by its kernel is as far as possible from integrable. In other words, that the differential of the one form, if you restrict it to the kernel, is a symplectic form on the distribution. Distribution here, as it is the kernel of one form, is a codimension one distribution. So the contact manifold. Well, this is a co-orientable contact manifold. Okay? So the distribution is contact, okay, but it comes from a specific choice of a global differential one form. Say that eta is a contact form. Okay, so that's the definition of a contact one form on a manifold. And again, some definitions that are well known. So in this situation, okay, so you have a vector field that you can define. Vector field is characterized that way, so it should be in the radical of this partial symplectic structure d theta. Okay, so the interior product of d theta should with psi should 0, and the second condition is a normalization condition, which is that when you evaluate theta on this field, you have always 1. So this is a vector field, okay, which is transverse to the distribution. And this vector field is always well defined, and it is called the RAPE vector field. And now let me pass to the sub-Riemannian condition. So we had this contact condition. Now there is in order to get a sub-Riemannian manifold structure, then you have to add some sub-Riemannian structure. So what is a sub-Riemannian structure in this case? This is a Riemannian metric, but only defined on the distribution. So I call this metric G. Okay. should be a section of the second symmetric tensor power of the distribution, and with itself. So when you have such a triple, okay, when you have such a triple, then you have what is called the contact sub-Riemannian manifold. So these are manifold that were considered already in the seminal work by Richards in 86 on the sub-Riemannian geometry. And these are very, very well studied, so particular in the context of pseudo-complex geometry. It's very, very well known, very rich situation. So this is what we are talking about. And so I define the object of the category. So now let me define the morphisms. Okay, morphisms are the ones that you are thinking about. So what is a sub-isometry? In this case, this is simply a diffeomorphism of the manifold, which preserves the distribution and the partial metric. Okay, so this is what is called a sub-isometry of M onto itself. Okay, of course, you can define the notion of isometry, sub-isometry between different manifolds, but it's not what I'm going to talk about here. So that's the definition of what is a sub-Riemannian contact manifold. So as far as we are now, so we have this definition of what is symmetric spaces, symplectic symmetric spaces, and now apparently completely different distribution, the definition of what is sub-Riemannian manifold in the contact situation. Good. And there is a very nice result due to Elisha Falbel and Claudio Gorotsky, which is the following, which is that on this, so also Michel Rumin is very, very close to that theorem. Okay, which is the following. So if you have a contact sub-Riemannian manifold, then you have a preferred connection. So which somehow plays the analogous role of the Levi-Civita connection in the case where G is a full metric on the manifold. So what is this theorem more precisely? You have a linear connection, okay, which preserve the distribution. Okay, so this is what is written here. Okay, that's the first item in the theorem. Okay, I'm saying that this connection is unique. Okay, so determined by the contact sub-Riemannian structure, which has the property that the Rabe field of the contact structure is parallel. The partial metric, of course, here it's on D. What I'm writing here is also parallel. And then the torsion. So this connection is not torsion free. Okay, the torsion defined here. I forgot to write where X and Y are. They are in the distribution. They are the vector fields and then tangent to the distribution here. Then the torsion. Okay, the torsion on D is actually proportional to the Rabe field. And the factor of proportionality is the evaluation of the symplectic structure on the X and Y. And now you can talk about the torsion with an element of D, for example, and the Rabe field, and this gives you an endomorphism of the distribution D, okay, of the contact distribution D, and this endomorphism plays a important role. This endomorphism is called the subtorsion. So basically, what tells this theorem is that you have some kind of Levi-Civita connection compatible with the linear the structure of sub-Riemannian contact manifold. but the compatibility which implies uniqueness has a price, and the price is that you have a torsion. And the proposition which is due to Falbel, Gorodsky, and also Daniel Tost is actually this is basically a direct consequence of Rajewski and show theorem that I was talking about in the case of CC manifold, so the Carnot-Carathéody manifold. But anyway, in this context, it is true that if you have any point in your manifold is connected, don't forget, then they can always be joined by a horizontal broken delta nabla geodesic. So they can always be joined by a curve which is horizontal. So gamma dot, if you want, if gamma is a curve, gamma dot is always tangent to D, inside D, and also which is geodesic. So in the sense that nabla gamma dot equals 0. Okay, so this is the proposition of Falbel and Gorodsky. And this is a basically direct consequence of the fact that the distribution is bracket generating. Okay, so this is a remark concerning the sub-Riemannian contact manifold. Okay, now let me go to a definition, which is again due to Strichart in 86. Okay, which is of course that in that situation you can define the notion of symmetric space, okay, which is analogous to the notion of Riemannian symmetric space. So you see here that the definition that I'm choosing here is not exactly in the same idea of loss. It's not exactly that. So sub-Riemannian contact symmetric space, okay, so is again sub-Riemannian contact manifold. So here M, E, and G, together with a multiplication. Okay, so this starts very much like loss. But then the map psi is required to be a sub-isometry. So this is not required in the case of loss. Okay, here it is required, and that fixes X, and such that on the tangent on the distribution, if you look at the tangent map of psi X, okay, so this thing that will play the role of sub isometrical symmetry. Such that this map, okay, it fixes X, so you can talk about the differential of psi X at point X. Okay, it's an endomorphism of dx. It should be minus the identity. So this is a priori stronger, okay, to the condition that simply that X is isolated. It is a different definition. So that's the notion of symmetric space, okay, in this sub-Riemannian contact category. Okay, that is a very classical notion, which is due to Strichart in that context. Okay, so now we have the notion of symplectic symmetric space, and now we have the notion of sub-Riemannian contact symmetric space. The first theorem that I would like to tell you about is is a theorem in a joint work with Falbel and Gorodsky, actually, which appeared in 1995. That's a very long time ago, and which was published in the Pacific Journal of Mathematics. So the theorem is the following. So if you take a sub-Riemannian contact symmetric space, and that in the sense that I just defined, okay, then you know from the theory that the Rape field is actually defines a vibration in circle or in real line over a symplectic manifold. So it's always, at least locally, this is always the case for any contact manifold. Okay, the Rape field defines a local vibration over a symplectic manifold. But what we proved is that actually in the sub-Riemannian contact symmetric space, this vibration is over a symplectic symmetric space in the sense that I defined. And that theorem allowed us to actually completely classify all sub-Riemannian contact symmetric spaces. And these are not, as in the case of Riemannian symmetric spaces, these are not always semi-simple spaces. So the classification is the following. From this theorem, it is quite easy to get to the following classification. You see, here, you have the following. So at first, as a sub-Riemannian contact symmetric space, you have a solvable example, which is this Heisenberg example that I showed you before. Okay, so this one appears in the classification as an isolated case of solvable manifold. Solvable manifold means that this is a homogeneous manifold such that the group is a solvable group. Here it's even nilpotent group. Okay. So then you have semi-simple examples. So first you have, as expected, you have Hermitian symmetric spaces. So basically you have what is written here, okay, S1 vibration over Hermitian Riemannian symmetric spaces. So these S1 vibration over Hermitian symmetric space is exactly what corresponds to pre-quantum bundles in the context of geometric quantization. Okay, so this is exactly what you have. And in both cases here, in those two examples, well, not examples, but on those, so example here is not a good word. I mean, we are really talking about the spaces, right? So I don't know why we wrote examples here. It's not example. It's exactly what the spaces are about. Okay, so in these two pieces, so there has this Heisenberg solvable and Hermitian symmetric space. The subtorsion vanishes. So, okay, this is very close to non-things. And now you have a non-Hermitian examples. Okay? So you have a simple example. So I mean G over K, okay, where the G is simply grouped. Which here you see you have here you recognize here the last one. You recognize, for example, the hyperbolic space. Okay, you recognize it here. Okay, so this is some kind of hyperbolic spaces. Okay, here you have a Euclidean one. Here you have the one. Okay, and here you have a one in signature and two. And there it is interesting to see that this subtorsion tensor that is defined by this canonical connection on the sub-Riemannian contact space that you have, okay, is non-zero. So these are really interesting examples from that point of view. And then you have non-simple examples that are also there. You see SO4 is non-simple It's semi-simple, it's decomposable. It's basically the algebra is SO3 plus SO3, and here you have SO22, which is algebra is SL2R plus SL2R. So you have these non-simple examples, but also interesting from the point of view that subtorsion doesn't vanish. And then here you have mixed examples, okay, which are very close, you see, to those Cartan motion group that I was talking about in my very first motivation section. Okay? You see, you have here groups that are, the first one is really a Cartan motion group. The other one is some kind of Lorentzian generalization of a Cartan motion group, which was not considered by Mackie in his conjecture, but still they appear here. So what it is, well, you see, let me talk about these ones, okay, in the non-compact factor case here. These are really Poincaré groups. Okay, so you see, really, this is the Poincaré group, quotient by this rotation group in the Lorentz group here, okay. And so you see here that it relates actually very much to these Klein-Gordon particles that I was talking about. So you consider the Klein-Gordon particle, okay? You consider its construction through orbit method, starting from massive orbits. And I told you that these massive orbits are, of course, symplectic spaces, are cohesion orbits. But I told you that they are symplectic symmetric space. So here, what you see is that this contact sub-Riemannian symmetric space, which is the one that fibers over the symmetric space, which is the Klein-Gordon one, is actually here present as a pre-quantum bundle. Okay, so this is already the pre-quantization of the Klein-Gordon that shows up here in this structure. And then you have other type of twisted product with the Heisenberg solvable examples and also Hermitian symmetric spaces here. But in these examples, the subtorsion is zero, so I'm not going to talk about that. Okay, so this is what is there. And now let me talk about, at last, let me talk about the theorem, which is the following. So you have precise definition now what is a kinematical Lie algebra, but slightly bit generalized. So we call them, with Nicolas Boulanger, we call them generic, okay? What is generic? Well, this is exactly what I told you. So you have SOD here, but here it's not SOD. This is any compact Lie algebra. Okay, you take any compact Lie algebra. You take any simple faithful K module, any faithful representation of K. In the case of classical kinematical Lie algebras, these were simply defining representation of SOD, so RD. But here you take any faithful representation and you put on the module, you put a condition, okay, which is that the isotopical component of the representation of K in the second antisymmetric power of the module, this should be empty. Okay, so in other words, lambda 2 of V does not contain V as a sub module. Okay, so this is what you have here as a condition which holds as soon as D, the SOD, as soon as D is greater than 4. And then also exactly as we had in the kinematical case, the line arc here, I call it Z, okay, and it should commute with the rotations which are here replaced by any compact Lie subalgebra of IG. Okay. This is what is called a generic kinematical Lie algebra. And the theorem is the following. So is actually that these structures of kinematical Lie algebras, which corresponds to relativity principles in the context of inertial observer, these are exactly sub-Riemannian contact symmetric space. So precisely, if you take a group simply connected, that admits such a generic kinematical Lie algebras, so I call them generic kinematical Lie group, then you have three things. The first is that G over K, so the K, which is the analytic group that admits K here as the algebra, analytic group of K. By analytic, I mean the connected. Actually, this is a sub-Riemannian contact symmetric space all the time. So this is not at all visible here in the definition, not at all. And it hasn't been seen in the physics literature. So this is actually a sub-Riemannian contact symmetric space. And the quotient, so the symplectic quotient I was talking about, as soon as you have a sub-Riemannian contact symmetric space, I told you in the first paper on 95 that it fibers over a symplectic symmetric space. Okay, so this is what we have. And the thing is that so this is basically what I said. Okay, and the thing is that if you take now, this is characterization of these kinematical Lie group and Lie algebras as among, I mean, sub-Riemannian contact symmetric space. Here, the two first points says that, okay, if you have a generic kinematical Lie group, then you have a sub-Riemannian contact symmetric space. But now you can ask the question, but what are the sub-Riemannian contact symmetric spaces that are coming from a generic kinematical Lie group? And this is those are the ones such that the horizontal holonomy of the sub-Riemannian structure is reducible. So I think I'm done. So if you have any question, please tell me.
Thank you very much, Pierre. That's very beautiful lecture. I wonder, you mentioned at the beginning that loss entity, this is start in 69 last century, and then you did work with Cartan and Good on symplectic symmetric spaces.
Yes.
Yes, in the 94, yes. And in 2000, you proved very beautiful formula.
Yeah, I proved it before. It was published in 2000.
But I'm surprised how, yes, I see. Yeah. So but did you use it reason in the later work on the symplectic symmetric spaces or somewhere else in this?
I think I didn't understand your question.
Did you use it result about the expression of the connection,
yes.
the linear connection somewhere
yes.
in later work?
Oh, this expression is used everywhere. I mean, so I knew it in my thesis, right? In 95.
So you know in your thesis.
Yeah, I knew it. It's published. It's published later, but I knew it. I knew it in my thesis, and many results in my thesis were actually used crucially this expression. Yes.
But I guess how to say he didn't think about this expression.
No, it is no, it is not. In fact, you see. This expression doesn't only hold for symmetric spaces. In fact, it holds for any connection. So if you have a connection, okay.
So then what is the S here?
yeah, so the S, if you have a connection, right? You have an say a linear connection. Then you can always find a map S, okay? A map S, at least locally. Well, you would talk about jets, okay? Here it's a very specific situation where you can integrate jets, but in general, you would talk about jets. But the message is that for any connection, any affine connection or linear connection, you can always find such a S, okay, local, let's say. You can always find such a map S. Locally defined around points, okay, such that the connection is written under that form. And when the torsion is zero, this map is exactly the geodesic symmetry map of the connection. That was somehow a question of Datry in the 80s, I think. So he was. He didn't say that, he didn't prove that at all, but he was somehow, I think, if you read under the lines in his papers, you see that he was somehow suspecting something like this. Datry. Datry. D apostrophe A T R E I.
Okay.
Datry.
Yes.
Yeah. The one from Datry spaces. I don't know if you know these things. This is okay. He's a Riemannian geometer, quite famous for certain things. But okay, so okay, so I think that answer a question of Datry.
Yeah.
Also, yeah. So it was really but Datry was really in the Riemannian setting. Okay, so here it's really it holds for any connection. You can always do that, always. And when the connection is with torsion, you can also write something like this. And a project would be certainly to write down. You see here, I'm talking really about symmetric spaces. I'm not talking about partial symmetric space as in the case of contact, okay, or sub-Riemannian. So I'm pretty sure that in the sub-Riemannian, situation, you have such kind of formula. You have such kind of formula where the S should be, it is not going to be that I'm sure. This is not going to be the geodesic symmetry in that case, but there should be an S, and that, I think this is an interesting problem in sub-Riemannian geometry to determine what are these what we call symmetry jets, that are attached to a connection that are compatible to sub-Riemannian structure, and even much more generally than just contact or contact symmetric. I mean, there should be some kind of general theorem there, and this should connect it. This should connect, I strongly believe, to the work of Jan Slovak. And no, I forgot the other collaborator, but okay. Recent work on holonomy of partial connections. So I think this is it's a very good question that what you are asking. But this map S is much more profound than just finding an expression. It's a nice formula and you can use it in symmetric space theory, that's for sure. But it's much more profound than that. And I think in the sub-Riemannian geometry, it should play a role, but it hasn't been established yet.
Yes, thank you, Pierre. Here.
Please, maybe some more questions, comments.
Yes.
Okay, so here, could you show the last definition?
Which one?
On the last page, on the page before that. No, here, this V.
Yes.
Isotypical component V in lambda 2V.
Yes.
Is it possible to describe this condition in terms of the Dynkin diagram using the labels?
yeah, I guess it is. Yeah. So right. Yeah, good question. Yeah. I think it basically what it says is that the V shouldn't be the Lie algebra of K.
So Lie brackets of those two V and V is
So
not allowed to take values again in V.
So what I'm saying is that K acts on itself, but the adjoint action.
Yeah.
K acts on its Lie algebra by the adjoint action. So the Lie algebra itself, if you look at if you consider the vector space underlying the Lie algebra, well, it is of course a K module. Okay? Suppose that even if K is simple Lie algebra, suppose, okay? So I think that this condition on the isotopical component, at least for SOD, this is exactly that. But I think more generally for a compact Lie subalgebra, I think it says exactly that this V, which is there, this module, okay, cannot be the adjoint representation of K. This is basically what it says. So your question is
okay.
Yeah, this is your question is yes. The answer is yes. I didn't formulate in terms of that, but I guess and I didn't prove it. In the case of SOD, this is evident, but in the case of a compact any compact Lie algebra, this is not this should be true.
Okay.
Yeah. Why are you asking this question?
Just it's interesting. No.
Okay. We can discuss maybe this question. Yeah. No, it's a good.
For example, if you consider tensor product of V and of Lie algebra K, tensor product. So what is the multiplicity of V in this tensor product?
Yeah.
So such question I was interested in. In fact, this number, this multiplicity is exactly the number of non-zero labels on the Zinkin diagram.
Yeah.
So
no, you are right. You are. I mean, this is. Yeah. That's what I thought you had in mind. But you are completely. That's very excellent question. So here, what you are saying somehow is that this definition is not general enough, and I totally agree with that. But we really wanted to connect with the notion of kinematical Lie algebra, which was introduced by physicists. So that's why. But you are totally right. I mean, there should be more general definition.
Okay, thank you. Okay. So maybe some other people have some questions or comments. No more questions. So thank you very much, Pierre.
Thank you very much.